Okay, so here we go. This is the first lesson I've recorded for trigonometry, so hopefully this will go well. It is over verifying trigonometric identities. Now we've spent a fair amount of time so far this year talking about trig identities, but we have not verified any to this point. Now when we verify a trig identity, what we're doing, it's also known as proving, I know you all love that word from geometry, trigonometric equations are true for all variables or all values of theta. Now I'm going to give you a number of hints and suggestions, but unfortunately, just like geometry proofs, there really is not one correct way to always do this. It's somewhat intuitive. It's like a puzzle. And the more of them you do, the better you're going to get at doing them. However, if you don't know certain things, you will have a very, very hard time with this. Now the first thing you absolutely have to know is you must know your fundamental identities. Now we've had several sets of those, but the big three are your reciprocal identities, your quotient identities, and your Pythagorean identities. On occasion, you may even need your cofunction or negative angle. There's a couple other sets we've already talked about, but these three are the big three: reciprocal, quotient, and Pythagorean. We went over all three of those sets of identities again in the section 5-1 notes, but we had covered them earlier in the book back in chapters 1, 2, and 3. The second hint that I will give you is that when you start, you always want to work on simplifying the more complex side of the identity. Now, that's subjective sometimes. Sometimes they're equally easy to do, but I think that most of the examples and most of the ones you're going to see on your homework, it will usually be easier to start with the left side of the identity. Now, the third hint is that sometimes, and it's really more like 75% of the time, you're going to need to take a certain approach, and that is to write everything in terms of cosine and sine, and then use algebra to simplify the expression. Now when I say write everything in terms of cosine and sine, that's going to use basically four of those identities. Those are that the secant is 1 over the cosine, that the cosecant is 1 over the sine, that the tangent, I'm running out of room so I'm not going to number these two, is sine over cosine, and that the cotangent is cosine over sine. Those four identities right there, that's 3 and that's 4, are used far more often than the others. Now, you also are going to use your Pythagorean identities quite a bit during this process, so you need to have all of your identities ready. But these four will be the ones you'll use to write the various terms in sine and cosine. Now, fourth thing you're going to need to know is that you're going to have to carry out several algebraic approaches on these trig expressions. The first thing you'll have to do is distribute. That does include FOILing, multiplying out polynomials. You might need to factor. That includes all types of factoring: difference of two squares, greatest common factor, trinomial. You might need to add or subtract rational expressions. Those are fractions. Remember that the big deal there is that you have to have a common denominator to do that. And then last but not least, you need to be prepared to reduce complex fractions. When I say that, I'm talking about a fraction such as, hold on one second, A over B over C over D. So a fraction within a fraction. You're going to need to know how to deal with that. Now remember that the goal is to make both sides of the trig equation Exactly the same, identical in every way, shape, and form. That means you're trying to make the left side equal the right side or the right side equal the left side. It doesn't technically matter which direction you go. So we're going to use those abbreviations. LS is going to be the left side of the equation. And RS is going to stand for the right side of the equation. Now, last but not least, remember, you are allowed to do any valid algebraic approach. That means you can cancel, you can multiply, you can divide, you can add, you can subtract, you can substitute. Anything you've been allowed to do with numbers and expressions in algebra, you are allowed to do while you're proving trig expressions. The big thing here is that your approach has to be valid. You cannot cancel illegally. You cannot multiply only one term by a value. Okay, unless you're doing something like rationalizing a denominator. I mean, there's a lot of things that we can do, a lot of tricks and shortcuts that we can use. So we're going to look through a number of examples. And when I say a number, I mean quite a few. Because this is a process that requires repetition to get good at. So here we go. Here's the first example. Now when we look at this, we should notice that the right side of the equation appears to be more complex than the left side. So we are going to start with the right side of the equation, which is actually fairly rare for the examples that we have written. So the first thing we do is we write RS equals, and we restate the right side of the equation. This is not negotiable. You have to be fairly formal in your solutions to these. They need to be organized, they need to be linear. So you'll notice I said right side equals, and then I wrote the expression. So now I'm going to write another equal sign, and I'm going to make some changes to that. Now we said earlier that our approach is going to be to turn everything into sine and cosine. So if we look of the three expressions in this statement, only one of them, cosecant, is not currently sine or cosine. Well, cosecant is 1 over sine. So what we're going to do is we're going to substitute 1 over sine in the place of that cosecant. And then we'll still leave everything else alone because everything else is already in terms of sine and cosine. So then our next step will be we're going to take 1 over sine and distribute. So when we do that, we get cosine over sine, because that's what happens when we multiply a number times a fraction. We end up with the number, which is cosine, on top of the fraction, sine, plus sine over sine. Now this is where our recognition comes in, because at this point, we are essentially done if we realize it. See, we have an expression right here, cosine over sine. Well, that is cotangent theta. So we are going to substitute cotangent theta for that first term. So cotangent theta. And the second term, sine over sine, well, those cancel. Now remember that if everything cancels, that doesn't make the term disappear. That makes it into a 1. So we have turned our original expression into cotangent plus 1, which is the left side of the equation. So we say equals left side, and that is how we complete the verification. We have shown in a linear fashion that the right side of the expression, through the use of proper valid algebra, is equal to the left side of the equation. That verifies that trig identity. Let's do another one. All right, so again, we need to make a decision. Which one is more complex? Now, many of you do not like fractions. However, I will tell you that this expression here is more complex than this expression. So we should start with the left side and turn it into the right side. So again, we start off, we rewrite the left side of that expression. So we write tangent squared x equals 1 plus cotangent squared x. There's a lot of ways that we could approach this. I think probably the easiest way would be to notice what's inside the parentheses. This expression, 1 plus cotangent squared, is one of our Pythagorean identities. It is equivalent to cosecant squared of x. So our first step should be to change 1 plus cotangent squared into cosecant squared. Now, at this point, what we should do next is change these expressions into sine and cosine. So tangent squared would be sine squared x over cosine squared x, because tangent is sine over cosine. So if I square it, that would square the sine and square the cosine as well. The same can be stated for cosecant. Cosecant of x is 1 over sine. So I can change cosecant squared into 1 over sine squared. So I'll go ahead and move myself down here, and I will say that tangent squared has become sine squared plus cosine squared. Sorry, sine squared x over cosine squared x. And we are multiplying that by 1 over sine squared x. Now when I multiply these fractions, what happens? Well, I have a sine squared on top and a sine squared on the bottom. So those would cancel. And then I would multiply straight across, which would give me 1 over cosine squared x. Now this is where we have a trick come up that comes up very, very, very often. And that has to do with cosine squared. We have in our Pythagorean identities the identity that cosine squared x plus sine squared x equals 1. Now if we rearrange that slightly by subtracting sine squared x from each side of the expression, then we can get that the cosine squared of x is 1 minus the sine squared of x. Now if we look at where we're at and where we're trying to go to, the only difference, we've got the 1 on top, but we don't have the right thing on the bottom. But we do have something that's equivalent to it. Cosine squared is equal to 1 minus sine squared. We just showed that right here. So what we're going to do to finish this problem, we're going to leave the 1 alone, and we're going to substitute in 1 minus sine squared x from here for this cosine x. That is equivalent to the right side of the expression, and that ends that verification. Now the notes that are posted online actually have 2 different versions of this verification. I did it another way that was longer, and then somebody pointed out this shorter way. So there's more than one correct answer for these problems 90% of the time. But one of those ways will always be shorter, and therefore not necessarily better, but more sought after. Moving on. Okay, so this one should be relatively obvious to tell which side is more complex. That would be the left side. So we are going to do the left side as our starting point, and we are going to turn it into the right side. So that's going to be our ending point. So the left side is tangent y minus cotangent y over sine y times cosine y. Now we're going to use a complex fraction to solve this problem. What we're going to do is our first step is we're going to substitute in our quotient identities. We're going to replace tangent with sine over cosine, and we're going to replace cotangent with cosine over sine. So that will give us sine. Actually, I would prefer that this were in blue, so let me fix that real quick. All right, let's try that again. Tangent becomes sine over cosine, and then we have minus, and cotangent becomes cosine over sine. Now I'm also going to go ahead and put that in parentheses because here in a minute we're going to multiply that by something. So I don't want you to think that we only have to multiply one thing. The bottom we're not going to change because everything there is already in terms of sine and cosine. I also just noticed that I instinctively changed all these thetas, all these variables into thetas. And they shouldn't be thetas, they should be y's because that's what's given in the problem. So let's change all of those now while we're thinking about it. Okay. Now, this is a fraction within a fraction. See, there's fractions here, and then the whole thing is a fraction. That's a complex fraction. Complex fractions are easy to deal with. All we have to do to deal with them is multiply the bottom and the top of the fraction by the reciprocal of the denominator. Now the reason we do this is because everything on the bottom will now cancel. Then what we do is we're going to distribute this expression back through into this hot mess of a set of parentheses. So bear with me here. Here's what that turns into. When we multiply this fraction by this fraction, the top is 1 times sine. So that's sine y over. And then the bottom is cosine times sine cosine. So that would be sine y times cosine squared y. Then we do this fraction times the second fraction. So 1 times cosine, so minus cosine y over sine y cosine y times sine y is sine squared y cosine y. You may want to pause the video for a minute and take that in. Alright, so from there, we need to notice that within each of these fractions, we have something that will cancel. We have a sine y over sine y, that will cancel. And we have a cosine y over cosine y, that will cancel. So this expression will turn into 1 over cosine squared y minus 1 over sine squared y. Well, 1 over cosine is secant. And 1 over sine, you guessed it, actually maybe you didn't, I don't know, is cosecant. So what we're going to do is replace that first term with secant squared y, and the second term with cosecant squared y. That is equivalent to the right side of the expression, and that ends the verification. I know what you're thinking, these keep getting harder. How hard are they going to get? Well, we are just about to the hardest one we're going to see. We have basically 2 or 3 more hard ones, then I'm going to do some easy ones just to show you that they're not all doom and gloom. Okay, now this expression is hard to verify because it's hard to tell which side of this expression is more complicated. The short answer is I would start with the more complex denominator in this case. So I would start with the left side and turn it into the right side. And to do that, we're going to use a relatively common algebra trick that we use to reduce expressions that contain a square root or a complex number I, because we're not allowed to leave that in the denominator. So what we do is we multiply by what is called the conjugate of the denominator, which would be 1 plus sine x. So we change that middle sign and we multiply. Now, if you notice, the other reason I'm doing this is because I'm trying to end up with 1 plus sine on top. And right here, right now, I've multiplied, this is multiplying by 1, so it doesn't change any values. But it puts a 1 plus sign on top of my fraction, which is what I've been shooting for in my final answer. So I'm not actually going to multiply those together. I'm going to leave the cosine out front, and again I tried to change it to theta. So cosine x times 1 plus sine x. But I am going to FOIL, multiply out this expression here. So that would be 1 times 1, which is 1. 1 times sine, which is sine x. Negative sine times 1 is negative sine x. And negative sine times positive sine, which is negative sine squared x. Now remember that once you FOIL, you usually have something that will do what? Well, cancel. These two terms right here will cancel each other out. So this would turn into cosine x times 1 plus sine x over 1 minus sine squared x. Now, depending on how good you are, you may have already noticed that same expression that we saw earlier where we had to solve for cosine squared x. It's one of the forms of one of our Pythagorean identities. Says that 1 minus sine squared is cosine squared. So we would replace the bottom of that fraction, so the top would not change, it would stay the same. We would replace the bottom of that expression with cosine squared x. Now if you look, we're getting closer and closer and closer to what we've been trying to reach, 1 plus sine x over cosine x. Here we have a cosine on top that we need to get rid of. But cosine on top and cosine squared on the bottom, the cosine will cancel into the bottom, which would eliminate the squared, and leave us with 1 plus sine x over cosine x, which is the right side of the expression, and ends our verification. Next example. Okay, so here we have one that is a higher exponent than we are used to. This one actually might be easier for you than the previous one if you have any amount of interest or talent when it comes to factoring. We're going to start with the left side, and that will end up being the right side. So if we start with the left side of this expression, which is sine to the fourth theta minus cosine to the fourth theta, we should see, or hopefully would see, that that is a difference of two perfect squares. Sine to the fourth has a square root of sine squared. Cosine to the fourth has a square root of cosine squared. So that is a difference of two perfect squares, which means it will factor. So we're going to factor that into sine squared plus cosine squared and sine squared minus cosine squared. Now I know what you're thinking, how does that help me? How does that make things any better? Well, sine squared plus cosine squared is one of our Pythagorean identities. That equals 1. So this expression will drop out. Why? Because if this is 1 and I multiply it by anything, I'm left with anything. So that will drop out and leave sine squared theta minus cosine squared theta. Now, cosine squared theta is what we need to get rid of because our answer contains sine squared. So we're okay with the sine squared being there, which means we need to do something about this cosine squared. Well, we said earlier that cosine squared theta is 1 minus sine squared, right? So let's substitute 1 minus sine squared into the expression here, okay? We're going to do 1 minus sine squared theta in place of cosine theta. That would mean we need to distribute this negative to the 1 and to the sine squared theta. That would be sine squared theta minus 1 plus sine squared theta. Those two sine squareds are like terms. So that would allow us to combine them to write it as 2 sine squared theta minus 1, which is the right side of the expression. Okay. Moving on, here's the next one. So, we're going to make sure we do this the right way the first time, because in past years I've done this the hard way the first time. So when I look at this, I would say we need to start here with these fractions and end up with the exponents. Double check my notes. Yep, that's how we want to do this. So we'll start with the left side, which is cosine x over secant x plus sine x over cosecant x. Now hopefully we've done enough of these by now that I don't need to keep writing in what things are equivalent to, but I will anyway because these notes are designed to replace a lesson. Secant is going to get replaced with 1 over cosine because we're trying to turn everything into sine and cosine. And cosecant is going to turn into 1 over sine. So that will give us cosine x over 1 over cosine x plus, and you'll notice I left myself some work room, sine x over 1 over sine x. Oops, I want to put that in red, don't I? There we go. Those are complex fractions. So as we discussed earlier, to get rid of them, we're going to multiply by the reciprocal, which would be cosine for that fraction, and would be sine for this fraction. Again, the point of that is that this will cancel, and this will cancel. So this expression will turn into cosine squared x plus sine squared x. Now I would think by now, we've done it enough times in this lesson, we should realize that that is equivalent to 1. Now I know what you're thinking, God, that doesn't look anything like where I'm trying to go, but in reality it kind of does. The same way that we have been able to rearrange other expressions, we have an expression that relates what we're trying to get to. Tangent squared plus 1 equals secant squared. It is one of our Pythagorean identities. So just like we did with sine and cosine, we can rearrange that expression so that we get 1 by itself. So we can state that 1 is equal to secant squared x minus tangent squared x, which means we can replace 1 with secant squared x minus tangent squared x, which coincidentally is where we're trying to get, so our verification is over. Okay, so now we're through the hard ones. Let's look at some easier ones just so we have some examples to prove that, this isn't necessarily the devil. Okay, I think there's a total of 3 easy ones here on the end. I'll do these much faster. So obviously we should see that the left side of the expression is the more complex side, which would be cotangent theta over cosecant theta. We should go in and replace those with their sine and cosine equivalents. So that's cosine theta over sine theta is equivalent to cotangent, and 1 over sine theta is equivalent to cosecant theta. We would then multiply by the reciprocal of the denominator to get rid of the complex fraction, which would be sine. All of this would cancel, as well as the sines would cancel, leaving us with only cosine theta, which is the right side of the expression. That one's done. On the next problem here, again, we should see the left side as the more complex side. So 1 minus sine squared theta over cosine squared theta, cosine theta. We are going to replace the top of this expression using that same trick we've been using over and over again. 1 minus sine squared is equivalent to cosine squared. So we're going to substitute cosine squared theta into that expression. That would give us cosine squared theta over cosine theta. Well, that would cancel. The exponent would cancel with the cosine on the bottom, leaving cosine theta, which is the right side of the expression. Final example. Here we have, again, a very obvious, simpler side. So we're going to start with the more complex side, which would be the left side of the expression. Cosine squared is equal to tangent squared plus 1, or times tangent squared plus 1. So what we're going to do is we're going to realize, hopefully, that tangent squared plus 1 is equivalent to secant squared. It's one of our Pythagorean identities. So that would allow us to change this into cosine squared theta times secant squared theta. Then we are going to replace secant theta, in this case secant squared theta, with 1 over cosine squared theta. So that would give us cosine squared theta times 1 over cosine squared theta, which would cancel and leave us with 1, which is the right side of the expression. Now, even though we finished these notes, you need to understand that these notes contain a number of examples, but they do not by any means cover everything that could come up on this topic. It is an extremely difficult topic, so you cannot hesitate to ask questions if you have them. Good luck on your homework.